This is the second integration lesson, integration 2, which will look at some standard integrals. In this lesson, you'll practice integrating different types of functions, and you'll use integration to solve some word problems. If you remember, back to the integration 1 lesson, you've learned some basic integration techniques and patterns. You learned the power rule with integration. You learned the constant rule, the constant multiple rule, and the rule for sum and difference. Today we're going to learn some other rules. The first rules that we're going to look at here are, you should recognize these. So the first one is integral of 1 over x, which is ln x. And the second rule is the rule for e to the x. Just like its derivative, e is its own derivative, e is also then its own integral. And the integral rule is e to the x plus c. So the top 2 boxes here are your basic rules for both ln and e. And the box on the bottom involves linear arguments. And that means the part in parentheses is a linear expression. Again, notice what happens. If the argument is linear, the rule is the same, as you can see in the first example, except what you're also going to do is you need to divide by the coefficient of a in the linear expression. In the second example, the example with integral e, again, e is raised to a linear expression. Again, the integral of e is itself, but again, you must divide by the coefficient of x, which is a in this case, 1 over a. In the same thing in the third example, the expression in the denominator is linear, so its integral will be ln, and it's ln of that linear expression, but again, you must also remember to divide by the coefficient of x. So those are your rules for e and ln, but also with a linear argument. We'll try a few examples. So in the first example here, we'll combine some of the rules that we learned in the last lesson. So I might rewrite this first example as 3, take out the constant, and then integral 4 minus 2x to the 5 dx. I'll keep the constant in front. I'm going to integrate the 4 minus 2x portion, and again that part will stay in parentheses, stays the same, and you apply the power rule. So we raise the exponent by 1, and as we learned last day, you must also then divide by that new exponent. And from what we've learned today, in addition, we must also multiply by 1 over the coefficient of x. So this is how it would look. And again, don't forget, with these indefinite integrals, we need to include plus c. Now you can see that this is 3 over 1 in front. We can cancel the 3 with the 6, leaves 2. So our final answer here is negative 1 over 4, 4 minus 2x to the 6 plus c. And don't forget, you can always check your answers from integration by finding the derivative or taking the derivative. In the next example, again I might take out the constant 2 and leave this as the integral of 1 over 3x plus 1 dx. And again, the constant multiple will stay. The rule for 1 over a linear expression is ln. So I know that'll be ln of that linear argument. So 3x plus 1, that part stays together. And new thing again that we've learned in addition is we must divide by the coefficient of x. And again, these are indefinite integrals, so include the plus c at the end. So now our final answer should be 2/3 ln 3x plus 1 plus c. To the next page for a couple more examples. In these cases, these also involve e, but you can tell that they're also using the sum and difference rule. Again, a way that you could rewrite this is you can write each of these integrals individually. So 4x, integral 4x dx minus, and again, I'll just take out the constant right away, so make that minus 2 integral e to the 1/3 x dx. Don't forget the dx. Dx is very important as well. Now, integrating 4x, again using the power rule, we'll raise the exponent by 1, so that becomes 4x squared, and we'll divide by the new exponent, 2. And for the second term, the constant multiple, again, will remain. And the integral of e, again, is itself, so it's e to the 1/3 x. Again, don't forget, 1/3 x is also a linear expression, so we must divide by the coefficient of x, so 1 over 1/3. And again, even though there's two terms, you only include 1 plus c. The c represents all constant in the question. This can be simplified a little bit. This is now 2x squared minus 6 e to the 1/3 x plus c. And that question is complete. Now on to the next one. Again, it might be worthwhile. You don't have to, but you can do this. You can separate the terms. This is equal to integral e to the negative 4x dx plus, I might rewrite this at the same time, integral 3x plus 2 to the 1/5 dx. And now we'll take the integral of each of these terms separately. So again, the integral of e itself, so e to the negative 4x, but again, negative 4x is a linear argument, so it must be 1 over the coefficient of x in front, 1 over negative 4. In the second term, in this expression, it's just the power rule again. So we're going to have 3x plus 2. We'll add 1 to the exponent. The exponent is 1/5. Adding 1 gives us 6/5. And now in front, we divide by that new exponent. The rule for power rule is divide by the new exponent, so 1 over 6 over 5. And again, because 3x plus 2 is linear, we also have to divide by the coefficient of x. And again, we'll include 1c for both terms. Again, this can be simplified a little bit. We have negative 1/4 e to the negative 4x. This is plus 1/3. 1 over 6/5 becomes 5/6. 3x plus 2 to the 6/5 plus c. And we'll rewrite the final answer. Negative 1/4 e to the negative 4x plus 5/18, 3x plus 2 to the 6/5 plus c. And that's the final answer. And we'll do one more example, the word problem. This question says the rate of change of a radioactive substance Q is given by, well, this should say Q prime. The rate of change obviously is a derivative function. So Q prime is equal to negative 200 Ke to the negative Kt. Initially there were 200 milligrams of this substance. If the half-life of this substance is 1200 years, find the amount of the substance left after 2000 years. So again, the question's asking about the amount of substance or the quantity of the substance. All we have right now is we have the rate of change of the substance. So again, to find Q at t function, we want the integral of the derivative function, integral of Q prime to dt if you want. So now we can write Q at t is going to equal, we'll substitute in the function now, negative 200 ke to the negative kt. I'll also apply the constant multiple rule in here. So this would be negative 200k integral e to the negative kt. Also realize that t is our only variable, k is a constant in this case. And again, we're really just, I should have dt in here. We're really just integrating the function e to the negative kt with the constant negative 200k in front. So negative 200k, the integral of e is itself, negative kt. And again, kt is a linear expression, so we also need to divide by the coefficient of t, so divide by negative k. In front here now, the negatives will cancel, the k's will cancel. So our final function for q at t is 200 e to the negative kt plus c. Need to include the plus c. Very important here. All right. So now the question says, if the half-life of the substance is 1200 years, find the amount of the substance left after 2000. Well, obviously we also need to find the value for k. We know that initially there was 200, and we know the half-life is 1200 years. So what we can do is into the function for q of t, we know the half of the substance will be 100. We want to find out what the k value will be, and we know that the t is 1200, so negative 1200k. This will be 0.5 is equal to e to the negative 1200k. Actually, I'll rewrite this as 1/2. It's the same thing. And now we'll take ln on both sides. So we'll have negative 1200k will equal ln 1/2. And so k, over here I'll just remind you that ln of 1/2 is equal to negative ln 2. You can figure that one out for yourself. And now dividing by 1200 on both sides, you get k is equal to negative ln 2 over 1200. And now, because we know the k value, we can actually solve for the quantity of the substance at time 2000 years is equal to, substitute in the things that we know, e to the, I'll leave the k as an exact value, negative ln 2 over 2000, over 1200, sorry, times the time 2000, all right? This can be simplified to 200e to the negative 5/3 ln 2. And when you punch that in your calculator, you should get 62.996 milligrams, which can be rounded to 3 significant figures as 63.0 milligrams. And that concludes today's online lesson for integration lesson number 2.